Okay, are we live? Hello, hello, hello. So I wanted to take a look at the next question. And give me just a moment here. Excuse me. So this question is going to be just another medium question. Yeah, we'll just get into it, I guess. Or we'll do that. We'll do that. So, increasing triplet subsequence. Let's take a look. Given an integer array nums, return true if there exists a triple of indices I, j, k such that I is less than j less than k, and nums of I is less than nums of j and less than nums of k. If no such indices exist, return false. Alright, so I think we do this in linear time, I believe. Interesting question. I don't actually know the solution offhand. I want to say you could do this in linear time. Let's think about it for a few minutes though before we start coding and start, excuse me, running my mouth. So, okay, so one way of doing this is cubic time, probably the slowest way, the naive approach where you just take a loop through all possible triplets and then check for all those triplets, those two conditions. You can do it that way. That would be like the simplest way to do it, but very slow if you do it that way. Now, we could, there is a solution. So we solved a problem similar to this, which was finding the largest increasing subsequence of an array, similar to this question. And we could actually just literally run that routine, the same problem, same question, and then take the, what do they call that? Take the, check if that's larger than 3, that's greater than or equal to 3. And that was a pretty interesting question and a pretty interesting solution. What you would do is you have an array of a vector of numbers. So it's linear, what do they call it? Linear space, extra space. And what you would do is you would say, okay, you find a number, it's going to be, you want the, at each index, you want the sequence. So at index 0 through 1, 2, 3 is sort of what you're going to have in memory. They're going to represent the size of the sequences. And the numbers at those indices are going to be the largest number that sequence ends with, or the smallest number that sequence ends with. So the sequence that has 0 elements is the minimum of all the numbers, right? It's just it's sort of the int min, sort of like negative infinity. And then once you see a number, then that becomes the smallest number for the first spot. And then when you see another number, if it's smaller, then that becomes again the smallest number for this first spot. If it's larger, then that becomes you actually go to the next slot down, which is index 2, and you would make it that number if you see the larger number. And what ends up happening is that you can actually, when you see each number, you can do a logarithmic search, a binary search, through your vector of numbers that you're maintaining to find where this number should be, if it should be added. And if it goes off the edge, you actually add a new piece to your vector, to your array, and write that number in. That's if it's larger. That's where you basically right. You do a binary search to find out where it belongs, and you would update that part of the array, or that part of the vector. It's a sorted vector, so you don't need to. It'll stay sorted the whole way through. So that gives you n log n time and linear space, and that'll give you basically the size of the vector at the end. If you're sort of growing your vector as you go, you just take that. If that size is greater than or equal to 3, then this is a, I don't know if this is duplicates, by the way. I'm actually not sure how this would work if there were duplicates or not. You can do it that way, as I just described, and then just return whether or not the remaining vector is greater than or equal to 3. There is a small caveat here with regard to largest increasing subsequence versus largest non-decreasing subsequence, and whether or not you're allowed to have duplicates in here. So yeah, that's yeah. Yeah, it's a little different. Yeah, you kind of have to finagle a little bit if you're doing non-decreasing versus increasing versus duplicates or not duplicates. But in any case, that's one way. That's n log n time with linear extra space, and that would solve this problem relatively efficiently. However, there may be a way to do this because you only need to consider 3 numbers. There may be a way to do this that's linear time and doesn't use any extra memory. So let's try coding up the one that I just described. Let's give that a shot, see where we go, see if we can solve it, and then we'll try the other approach. So we're going to say a vector of integers, and that's going to be what do you want to call this? It's going to be this. It's going to be the smallest. I think I just called it v last time because it's kind of hard to describe what it is. And you're going to say for auto x in nums, you're going to take standard. You want the upper bound, I believe, of v dot begin, v dot end. Call this auto it. And v initially it's going to be size 1 and int min. You actually don't need to do that. That's not even necessary, by the way. Upper bound, and the value is going to be x, right? Let me say if x is equal to, it's not equal to the end, then we're going to update that spot with, now so upper bound and lower bound are a little bit different. So lower bound I think is the first value that's greater than or equal to, and upper bound is the first value that's greater than. I just got to think about this for a minute. Upper bound is the first value. You're looking for the first value there's greater than and there's greater than or equal to. We want the first value that's greater than. If it's equal, we can just update it. Yeah, greater than or equal to. I don't know if upper bound's greater than or equal to. I don't recall. I don't remember that. That's like something I think I'll end up memorizing after a while. But I've done that like multiple times. Oh, no, that's not the right one. Lower bound, let's do that one. Greater than or equal to is lower bound. Yeah, so we actually want lower bound, I believe. And we'll say if it's not equal to the end, then we're going to take that value and update it to x. Otherwise, we're going to take v and we're going to push back x. Something like this. And then we want to return that v.size is greater than or equal to 3. Something like this. Now, what we want to do also is index 0, index 1, index 2. Yeah, I think that's right. I want to say that's right. Yeah, okay. And, oops. 5, 4, 3, 2, 1. And we probably could think of some other examples. Just want to do a few tests. Oh, okay. One issue is, right, I'm glad we don't need to use int min. We can do it this way, because if we had to use int min, we'd run into problems here. Alright, we're gonna go for it. Let me just throw in a couple more random test cases. I'm kind of nervous. I think it's right, but I'm nervous anyway. There's probably some test case I'm not thinking of. You know, like I don't know. I don't even know what test case I could use to cause problems. If you're familiar with the word fuzzing, I kind of want to fuzz this. Try a whole bunch of random things to see if we... All right, let's go for it. Hey, got there. Sweet. Okay, yeah. I mean, that's pretty efficient, right? That's not too bad. 8 milliseconds. It's pretty quick. So, yeah. So that's what I was saying, is that there's kind of a very clever way to find the longest increasing subsequence, and then you can use that to actually check this problem. You can use that solution to also find a fairly efficient solution to this problem. That being said, you can do a little bit better than that, and you can say, you could do false, and you could terminate early. You could say if b.size is greater than or equal to 3, turn true. And that I think is going to be even faster. That's even faster. And we're approaching 100%. I'm wondering, this is actually still n log n, but this is now constant space complexity. But it's still O of n log n time. What I want to say is, I actually don't know. No, actually no, this is linear time. Yeah, awesome. No, this is efficient as you can get. I'm sorry. Cool. No, this is so cool, because the size of V is constant. It's only 3 elements. This routine is actually constant time. So actually the whole algorithm is constant time. Oh, I feel so smart. I actually didn't even have to try that hard. That's so cool. So this is actually linear time. So this is as efficient as you can do it. Wow. That's great. Cool. We did it. We did it. Yeah. Oh, let me see if I get 100%. There we go. Boom. 0 milliseconds. How about that? How you like them apples? All right. Hopefully the explanation made some sense. I've explained it in a previous video, but basically, this array that you've got is just going to keep track of, like, it's actually kind of shifted over a little bit. So like the 0 index is going to be the smallest number of a subsequence of size. Subsequence of size 1 is the smallest number at the end of any subsequence of size 1. Of all the subsequences of size 1, it's the smallest ending number. And then for the next number in the array is index 1. That's going to be subsequences of size 2, right? 1 plus 1 to give you 2, or add 1 to get the index plus 1 to give you 2. And that's going to be for all of the subsequences of size 2. That's the smallest number up to this point that those subsequences of size 2 end with that number. And basically, you realize that you only need to keep track of those numbers because of that many of those numbers, because at that point, if there's any number that you might add to any of these subsequences, obviously you want to create the next larger subsequence size. So like if you had a subsequence size 2, you want to get to 3. If you have size 1, you want to get to 2. If you have size 3, you want to get to 4. And the optimal at that point is to keep track of just the subsequences with the smallest numbers at the end. And you don't even care what came before it. You just care what you ended with. And then you can add the next number and say, oh, since this new number is larger than such and such subsequence, now we have sort of the next, we can update that. And in fact, if you are larger than if you're between two things, then that actually means you actually want to update the one that's greater than or equal to gets updated because that basically the subsequence that came before it is now going to update to it, if that makes sense. So in other words, if you have like ending with 5 and ending with 10 for a subsequence of 100 and a subsequence of 101, so 100 ends with 5 and 101 ends with 10, when you add a 9 to the 100 that ends with a 5, you get 101 that ends with a 9 instead of a 10. So you update exactly the value that's greater than or equal to gets updated with the new value. And if you go off the edge, that means that you have something larger than all the numbers, and so actually your largest subsequence can now be increased by one value, so you append it. And actually keeping everything bounded by size 3 makes this routine constant, and also makes the amount of memory we're using constant, so this is a linear time solution. Awesome. Wow, that was super quick, super simple, super easy. Heck yeah. This is like, see, if you came across a problem like this in an interview, how quickly you could code that, how fast you could do that, and you'd seem like such a genius, because if you hadn't seen this question before, like, it's a pretty hard question, in my opinion. It's like a relatively pretty challenging question. So awesome. So yeah, just gotta spend that time. All right. Well, thanks for watching, and I'm gonna go ahead and go to the next problem. Take care. Take care. Hope that was enjoyable. Hope that was edifying, interesting.